Hello and welcome to my presentation. My name is Tourlidakis and I'm a fourth-year undergraduate pharmacy student in the University of Nottingham. I undertook my third-year project in the International Space University in France, and basically it looked at investigating Meloxicam utilization in space and its effects on planarians in a low magnetic field. My project supervisors were Professor Virginia Watering, who is based in the International Space University in France, and Dr. Lee Chanteau, based in the University of Nottingham here in England. So, the outline of this presentation. I will introduce you with some previous work done related to medication use in space, non-steroidal anti-inflammatory drugs, as Meloxicam is one, planarian nociception and magnetoreception. Then the materials and methods used for this project will be discussed. Experimental results and analysis will also be noted, and the discussion of the results and comparisons with previous work done in this field are included in this presentation, including strengths and limitations of this study. Finally, conclusions of present work will be drawn and suggestions for future studies will be noted. So let's start with medication use in space. So during spaceflight missions, astronauts use medications for a variety of indications, either preventing or treating health issues that have arisen due to the unfamiliar spaceflight environment. So in space, there are many physiological stressors that exist. Some include space radiation, isolation and confinement, distance from Earth, gravity fields, hostile and enclosed environments, and all these can alter the way the body functions. Also, another indication of using medications in space is to treat typical minor ailments. Pain that astronauts experience can include muscle pain, back pain, joint pain, and headaches. Actually, muscle pain and back pain are most commonly caused due to the resistive exercise device that astronauts use for bone preservation. Another cause of pain can also be the EVA suit that leads to astronauts potentially taking prophylactic medication to manage their symptoms. Headaches also are very prevalent in space, and this can be due to pressure changes or carbon dioxide levels being extremely high. Other causes may include hemodynamic changes, cephalid fluid shifts, and other causes. So NSAIDs, non-steroidal anti-inflammatory drugs, are essentially the most used medications in space, with ibuprofen being the first choice. So other NSAIDs used in the IHS include paracetamol. Planarians. So planarians are aquatic animals, they're flatworms, and their brain has structural and molecular similarities with the mammalian brain. This allows neurodevelopmental toxicity relevant to humans to be determined. Their nervous system and neurotransmitters are also very similar to higher order organisms. Also, they have extraordinary regenerative abilities driven by planarian neoblasts. So essentially, large numbers of neoblasts can be found all over the planarian parenchyma, making planarians a desirable model for stem cell biology and regeneration studies. Planarians present three main types of behaviors. Colliding, which is usually the normal behavior with the cilia beating in a layer of secreted mucus. So basically the cilia beats in synchrony, creating metachronal waves. And when planarian glide, they're elongated and do not have any net deformations. So essentially they're just swimming across. Scrunching is a form of planarian locomotion that is basically defined by asymmetric body oscillation. And it's usually musculature driven, and it's the planarian's capacity to respond to adverse environmental stimuli. So there is a hypothesis that has been made that during scrunching, essentially what happens is the planarian secretes an excess of mucus, and this can act as a protective barrier in response to noxious stimuli. So noxious stimuli can include high temperatures, low pH, amputation, UV lights, and electrical stimulation. So there seems to be indeed a correlation between extreme excess mucus production and scrunching. Peristalsis is also musculature-driven. It occurs when the cilia beating is impaired and is based on contractile waves being propagated in the muscular tube. So just to show what scrunching is essentially the planarians, instead of swimming as they did before, they go like that in the water, so they scrunch. So planarian use in research actually has many advantages. Planarians are small and low cost to maintain, and also they're quite easy to breed in a laboratory. You can use a large sample size, and planarians have a wide range of observable behaviors. Also, the aquatic environment allows rapid and easy exposure to chemicals and drugs. There is no genetic variability between adult and baby planarians, and also planarians are invertebrates, thus there is no ethical dilemma. Meloxicam. So Meloxicam is a long-acting non-steroidal anti-inflammatory drug that is used for pain relief. It's usually used for osteoarthritis and rheumatoid arthritis. And essentially, its mode of action is via prostaglandin H2 synthase, also known as COX inhibition. So this process basically does not allow arachidonic acid present in the phospholipid membrane to be converted into prostanoids, which are inflammatory mediators, thus reducing inflammation. No reports actually exist on meloxicam previously being used in spaceflight. However, it is the NSAID that was selected for this study because meloxicam was used in a paper by Kim and Rolls, which was actually out in 2022. This particular selection would allow comparisons to be made in the discussion part of this project, and also other NSAIDs have been used in spaceflight. Thus, this study paves the way for testing other NSAIDs. Future long-distance interplanetary flights, it is suggested that the human body will undergo a magnetic field exposure that's about 10,000 times weaker than the one that's on Earth. So essentially, the Earth's magnetic field forms a protective layer that traps and repels solar charged particles. Thus, space's greatly reduced magnetic field can cause the body to handle medication differently. Essentially, the geomagnetic field is about 50 microtesla, and the hypomagnetic field is significantly lower. Also, because the hypomagnetic field is variable, it has fluctuations. The definitive value of the hypomagnetic field is always relative to the time that it was taken. So essentially, the aim of this study was to determine whether Earth's magnetic field has a role on the analgesic effects of meloxicam. So let's see how we performed this study. So the test animals and their maintenance. So essentially, freshwater planarians of the Gerardia digrina species were used for all the experiments which were conducted in the present study. So as you can see on the right of the slide, there is an image that we actually took in the laboratory of planarian. And the planarian in this image is about 1.5 centimeters long, so they're quite small animals. Planarians were kept in glass storage containers containing volvic water, which is browns of natural mineral water. And before using them in experiments, they were not fed for at least 5 days to starve them. And 12 planarians were used for each different test and concentration that we performed. So the chemicals that were used for this experiment were our drug, meloxicam. Isothiocyanate is basically AITC, which is mustard oil, which was used as the pain condition that planarians were put into, and natural mineral water was also used. So here is a summary of all the tests conducted for this study. So you can see meloxicam concentration and whether mustard oil, i.e. the pain condition, was present, and also the magnetic field condition. So you can see that all tests were also done in both the geomagnetic and hypomagnetic field, with the first 4 tests being performed as control tests. And yeah, in 1, 3, 10, and 100 micromolar meloxicam concentration were used. So here you can see the magnetic field chambers that we made for our experiments. So planarians were basically incubated in meloxicam in different concentrations for 2 hours in either the low magnetic field box, which we actually measured the magnetic field in that box to be 2 microtesla. So this box was actually made using a Tupperware, plastic Tupperware box, which was covered with a mu metal, which is a nickel alloy that provides magnetic shielding. And also, as a control box, we also did similarly, but we used aluminum foil to cover the plastic container. And the magnetic field in that box was actually found to be, was found to be 45 microtesla. So this box actually acted as control. So yeah. So after the 2 hours of incubation in either the hypomagnetic or the geomagnetic field box, the planarians were, one planarian at a time was placed in an arena containing 50 micromolars of AITC, i.e. the pain condition, and the worm's locomotion was recorded in complete darkness for 5 minutes using the behavior rig that you can see in this photo. So as you can see, the components of this behavior rig include a Faraday cage, which is based on a vibration isolating tennis ball platform, so that planarian behavior is not influenced by noise and ground shaking disturbances. So this cage was created using PVC pipes and radio frequency shielding plastic. Inside the cage, the arena that would be recorded was placed on a stand created by PVC pipes and 2 square wooden bases. On the top of the Faraday case, an infrared cut camera was placed in the middle of a plastic rig that had infrared strip lights fixed to it. The camera was also connected to a Raspberry Pi 4, to which a monitor, mouse, and keyboard were also connected. The Faraday cage was connected to ground, allowing the electrical charge to exit, and the planarian was recorded in the arena using 1 frame per second. Once the recording was finished, essentially the planarian was removed from the arena using a pipette. The AITC solution was changed for every worm to avoid possible stress compounds being released in the solution influencing the next worms. And the arena was basically washed with alcohol and rinsed a couple of times before used again to avoid sticky mucus remaining on the glass. So the video analysis and modeling tool that was used is called Tracker software by Quizlet. So it's freely available, and it's based on the open source physics Java framework. So this program essentially allows me to manually track the animal. So what would happen was I went and tracked the animal at 10 frames per second. So I clicked to the path that the animal followed every second. So ways do exist to make planarian tracking automatic. However, this would not work well with objects moving quite randomly and continuously changing their shape, especially with a video of relatively low contrast. So it was much faster to manually track the animals. However, 144 animals were used, so this was quite a strenuous process. So the behavioral phenotypes included gliding, which is basically the normal planarian behaviors, just swimming; scrunching, which is the response to adverse stimuli, which in this case was AITC, the pain condition; C shapes, which are like planarians forming a C in the arena; Screw-like movements were essentially planarians putting their head up towards the surface of the water, the ITC solution or water, sorry. But we also had head shaking, frequent turns, and abnormal lung body elongation. So after tracking the animal to find its distance traveled, a video player program, VLC, was actually used to actually determine the fraction of time the planarian performs each behavior. So essentially what I would do is I would say from 0 to 10 seconds, the planarian glided. From 11, let's say, to 20, it scrunched, and so on. And then I would divide the amount of seconds to the total amount that the video was recorded, i.e. 300 seconds, to actually find the percentage of each behavior in total. So statistical analysis and data plotting. So yeah, so essentially the percentage of worms exhibiting gliding, scrunching, or other behaviors was used to determine the significance, and error bars were created as the standard mean error. The rate of movement, i.e. the speed, was found using the distance traveled by the planarian, which was found using the tracker software, but we divided this by the total recording time. Afterwards, a statistical two-sample student t-test was performed to pairwise compare planarians based on the hypomagnetic and geomagnetic fields. And Microsoft Excel was used to perform statistical analysis with a value of 0.05, with a p-value less than 0.05 considered significant. So some results. So as you can see in this graph, essentially this graph shows the speeds and the meloxicam concentration. So as we increase the meloxicam concentration, how did the planarian speed change? So there seems to be a decrease in the speed of a planarian. And actually, there was a statistical significance found at the meloxicam concentration of 100 micromolar, which shows a significant difference between the hypomagnetic and geomagnetic fields. So essentially, you can also see the average speed when exposed to the geomagnetic fields and hypomagnetic fields in this table. So you can see that no solid conclusions can be made, but there seems to be that the planarians that were placed in the hypomagnetic field had traveled quicker than those in the geomagnetic field, especially at 100 micromolar concentration. But no solid conclusions can be made for the speed of the planarians. What's more exciting is the following slides, which are based on planarian behavior. So as you can see here, sorry, I'll just do my. So as you can see here, as we increase meloxicam concentration, the gliding of the planarians, i.e. their normal behavior, actually increased as well. There was a higher overall gliding behavior on the hypomagnetic field than the geomagnetic field. As you can see from the graph, all the yellow histogram bars are actually higher for the hypomagnetic than the lower. And also there was found to be a significant difference at gliding at 100 micromolar concentration. And this actually is supported by the following slide as well. So scrunching behavior. So essentially, as we increased meloxicam concentration, scrunching decreased. So there was found to be a concentration-dependent decrease in scrunching. And as you can see, scrunching was less in the hypomagnetic, in planarians placed on the hypomagnetic field chamber than planarians placed on the geomagnetic field chamber, sorry. So the other behaviors the planarian showed, as you can see, sorry, so the other movements included the C-shapes, the screw-like movements, rapid head turning, etc. No concentration-dependent effects on other planarian behaviors was actually observed, and there was no significant difference found. But as you can see also, as meloxicam concentration increased, it seemed to be that other behaviors also increased. And here you can see combined graphs of the geomagnetic field exposure on the left and the hypomagnetic field exposure on the right. So as you can see, essentially, it's what we said on the previous slides. As meloxicam concentration increased, gliding increased, as you can see on the green bars and on the yellow bars also, and scrunching decreased. So, discussion. So, Human rules papers that I also mentioned in previous slides, the 2022 paper, basically looked, they tested whether meloxicam will reduce nicotine-induced C shapes, as C shapes may have a potential role in pain. And they found that planarian exposure to 10 or 100 micromolars meloxicam concentration displayed a reduced number of C shapes. So this paper actually supports our results. As meloxicam concentration was increased, enhanced analgesia was observed in planarian behavior. So essentially in our study, what we said was that gliding, we considered the planarian not to be in pain. Scrunching, we considered the planarian to be in pain. And the other behaviors, we actually do not know. So we do not know whether they were or were not in pain. So we did not focus that much on other behaviors. So limitation of this study, essentially only one planarian species was used, Gerardia tigerina. Scrunching regulation is actually poorly understood yet, so we're not sure if it's definite pain response. Also, it's unknown how much drug was taken up by each planarian. It was strenuous to distinguish by eye between scrunching and other behaviors because planarians actually changed quite rapidly their behavior whilst they were in mustard oil or in water. Planarian tracking was also prone to human error. And also there was, though we had 6 times out of 144 where the Raspberry Pi actually failed during the recording. So strengths of this study, they include a large sample of animals being tested. A consistent methodological approach was used for all animals. The planarians were tracked manually, thus there was a careful monitoring of each planarian. And also one scientist actually performed the categorization of the planarian behaviors. Thus, that was considered to be more fair than multiple scientists working on this. So we've finally got to the conclusions of this study. So magnetic shielding actually may provide enhanced analgesia. So there seems to be a mechanism by which the hypomagnetic field exposure potentiates the analgesic effects of meloxicam. Furthermore, this study offers new possibilities to combine the use of advanced planarian behavioral assays with space medication research. Future work, actually, we're planning to focus more on the effects of the Earth's magnetic field on other drugs. So, for example, opioids or other NSAIDs. And furthermore, this study can have the potential to improve the quality of life of patients by developing low magnetic field chambers on Earth for enhanced analgesia. So essentially, chambers with similar properties exist, and they're currently used in magnetoencephalopathy (MEG) studies. So ultimately, if humans have the capability of detecting hypomagnetic field changes, and methods are developed to manipulate that, then a big promise is being held on applying magnetic field shielding in physical therapies for pain relief. So currently, this whole study is being repeated by Professor Virginia Watering at the International Space University in France. So this will allow more data to be collected and analyzed, thus more solid conclusions to be made, and hopefully this information will be disseminated to the scientific community in the form of a scientific publication. So in the end, I would like to thank, and it was an honor to actually be supervised by Professor Virginia Watering in Strasbourg. I would also like to thank my Nottingham supervisor, Dr. Alicia Anto, who helped a lot in making this study actually true. Also, I would like to thank Professor Hervé Cadieux for his help and advice and support from the University of Strasbourg. And also, I would like to thank PhD student Guillaume Rehaut also for his help and support in this project. So thank you very much for your attention. And do you have any questions I can answer? Thank you.